Conditionally stable amplifier. In the previous video, we have discussed the stability of microwave amplifier, and we have said that the amplifier would be stable if the magnitude of gamma input is less than unity and the magnitude of gamma output is less than unity. And we said that the value of gamma input and gamma output depends on the source reflection coefficient gamma source and the load reflection coefficient gamma load and the scattering parameters of the transistor. And we have said that we can determine the location of the points where the source impedance and the load impedance, which correspond reflection coefficient gamma in and gamma output, are less than unity. And we said that this would be the stable region, and otherwise it would be in the unstable region. Now in this video we are going to test what is the condition for the stability. So if we have a simple expression to just determine this stable amplifier or unstable amplifier or conditionally stable amplifier. If it is unconditionally stable amplifier, it means that it is stable for any source impedance and any load impedance. If it is conditionally stable amplifier, it means that we have specific values for source impedance and load impedance, which will make this transistor as a stable amplifier. So the stability circles, which are discussed in the previous lecture, can be used to determine the region for gamma source and gamma load where the amplifier circuit will be conditionally stable. Generally speaking, if the magnitude of S11 or S22 are greater than unity, then the amplifier is conditionally stable. It cannot be unconditionally stable. It cannot be stable at any source and any load. So we have specific source and specific load which make the transistor in this case stable. So if S11 is greater than unity or S22 is greater than unity, the amplifier cannot be unconditionally stable because we can always have a source or load impedance Z0. In this case, the gamma input, it would be the magnitude of S11, and which is greater than unity, so it is unstable. If we are using gamma source equals 0 or gamma load equals 0, so this will cause gamma input would be the magnitude of S11, which is greater than unity, or S22, which is greater than unity. So if S11 is greater than unity or S22 is greater than unity, this amplifier is conditionally stable. We cannot make this amplifier unconditionally stable. Unconditionally, as I said, any source impedance, any load impedance can be used and the amplifier will be stable. No, in this case, specific source impedance and specific load impedance would be suitable to be stable. If the device is only conditionally stable, then operating points for gamma source and gamma load must be chosen to be in stable region. Otherwise, it would be unstable. And it is good in practice to check the stability at several frequencies over the range where the device is operating. As I said, the scattering parameters of the transistor itself, they are variable with the frequency. And gamma input and gamma output depends on the scattering parameters of the transistor. So if they are changing with the frequency, then the stability condition will be changing with the frequency. So it would be wise to study the stability of the amplifier at the operating frequency and at the frequency around this operating frequency. The scattering parameters of a transistor depends on the biasing condition. This is another case. And so the stability will also depend on the biasing condition. If the biasing condition is slightly changed, it will introduce change in the stability condition too. So if it is possible to accept design with less than maximum gain, a transistor can usually be made with unconditionally stable by using resistive loading. The resistive loading here is used to compensate any increase in the gain or any instability to make the amplifier in the stable region. But this will introduce some losses in this resistive part. So if we can reduce the gain or we can increase the losses slightly, we can improve the stability of the transistor. So if it is possible to accept design with less than maximum gain, a transistor can usually be made to be unconditionally stable by using resistive load. Now we have two tests for unconditional stability. The first test is called K delta test or related conditions. In K delta test, the value of K is 1 minus the magnitude of S11 squared minus the magnitude of S22 squared plus the magnitude of delta squared over 2 multiplied by the magnitude of S12, S21. This should be greater than unity. And should be this and. So these two conditions should be satisfied simultaneously. And delta, which is the magnitude of S11 multiplied by S22 minus S12 multiplied by S21, should be less than unity. So these two conditions simultaneously are satisfied to say that, okay, this amplifier or this transistor is unconditionally stable. Unconditionally stable, you will have any source impedance and any load impedance, and it will be stable. But if any one of these two conditions are not satisfied, it would be conditionally stable, and in this case, we should determine the stability circle for the load and the stability circle for the source, and from the stability circle of the load and the source, according to the value of S11 and the value of S22, we are going to determine which values of Z source and Z load will be stable and which values of Z source and Z load would be unstable. So these two conditions are necessary and sufficient for unconditional stability. Generally, we must have the magnitude of S11 is less than unity and S22 is less than unity. So basically, before studying any test for unconditional stability, we are looking for the magnitude of S11 and S22. They must be less than unity. If one of them is greater than unity, this means that this is conditionally stable amplifier. Alright? So we must have the magnitude of S11 is less than unity and S22 is less than unity if the device to be unconditionally stable. So before going to this test, at the beginning, look at the magnitude of S11 and S22. They must be less than unity. Effectively, this test is just unconditionally stable or not. If these two conditions are satisfied, this means that the transistor is unconditionally stable. If one of them is not satisfied, this means that this transistor is conditionally stable. But how much stability of the transistor? These two equations does not give us the answer for this question. The other test is the mu test for unconditional stability. The mu test is mu equals 1 minus the magnitude of S11 squared over the magnitude of S22 minus delta multiplied by S11 conjugate plus the magnitude of S12, S21. This should be greater than unity. So just one equation, and this value is greater than unity, is sufficient to be unconditionally stable. The advantage of this test is that if I have two values, assumes that I have a transistor with mu 1.5 and another transistor with mu 3.5, for example. The greater value of mu, the greater stability. So if mu is greater than unity, the device is unconditionally stable. On the other hand, larger values of mu implies greater stability. So the advantage of mu test for unconditional stability is that it implies not only the unconditional stability, but how much is the stability. So the greater value of mu the greater stability of the transistor. As an example, we say that we have a gallium nitride high electron mobility transistor with the following scattering parameters at a frequency 1.9 gigahertz. These scattering parameters are measured or calculated with respect to characteristic impedance 50 ohm. It is required to determine the stability condition of this transistor based on K delta test or and mu test. If it is unconditionally stable, it's okay. If it is conditionally stable, plot the stability circle on the Smith chart. Stability circles, which is stability gamma source and stability gamma load circle on the Smith chart. And from the stability circle, determine what is the range of Z source and Z load, which will correspond to the stable amplifier, and what is the range of Z source and Z load, which correspond to unstable amplifier. At the beginning, we look at the magnitude of S11 and S22. Fortunately, the magnitude of S11 and S22 are less than unity. This means that maybe this transistor could be unconditionally stable. Maybe, but I'm not sure. Okay? But if one of them are greater than unity, I'm sure it is conditionally stable. Okay? So, both of them are less than unity. So, maybe this transistor is unconditionally stable. And maybe not. To do this, we are going to calculate the value of delta and the value of K. The value of delta is S11, S22, S11 multiplied by S22 as complex quantities minus S12 multiplied by S21 as a complex quantity. Then this complex quantity minus this complex quantity is calculated. Then I'm going to take the magnitude of this value. By taking the magnitude, we will find that it is 0.336. Okay, the magnitude of delta is less than unity. One condition is satisfied. What about the second condition? The second condition is K is 1 minus the magnitude of S11 squared, which is 0.869, minus the magnitude of S22, which is 0.507, plus delta squared, which is 0.336 squared, over 2 multiplied by the magnitude of S12, S21. Here I'm going to multiply S12 by S21 as a complex quantities. Then I'm going to take the magnitude. Actually, this would be the magnitude of S12 multiplied by S21. Alright? By calculating this, we find that the magnitude of K is 0.383, which is less than unity. As I said, the unconditionally stable requires that the value of K is greater than unity and the value of delta is less than unity. But here the value of K is less than unity. So the magnitude of delta is less than unity, but the value of K is not greater than unity. So unconditional stability criteria are not satisfied, and this device is potentially unstable. This is from the point of view of K delta test. We can use mu test. Mu, it would be 1 minus the magnitude of S11 squared over S22 minus delta S11 conjugate plus S12, the magnitude of S12, S21. By taking this value, we obtain the magnitude of mu is 0.678, which is less than unity, which means that it doesn't satisfy the unconditional stability requirement. So, indicating that this mu, indicating that it is potentially unstable. So, effectively, this transistor is not unconditionally stable, it is conditionally stable. Conditionally stable means that we have range for source impedance and load impedance, which makes the transistor amplifier stable, and we have other range for Z source and Z load, which make the transistor is unstable. To determine the range for Z source and Z load, we are going to draw the stability circles for gamma source and gamma load. As we have discussed in the previous video, the center for the load circle, which correspond to uh, gamma gamma input equal unity, the center it would be S22 minus delta S11 conjugate, all of them is conjugate, over S22 squared minus delta squared. We have already calculated delta. So according to the S parameters here and the value of delta, we determine the center of the load impedance at the point 1.59 with an angle 132. And the radius for the load impedance is the magnitude of S12 multiplied by S21 over S22 squared minus delta squared. By using these S parameters, we find that the load radius, or the circle of the load radius, is 0.915. From these two values, we are going to draw gamma input equal unity for the load circle. So we are going to draw the load circle stability. The load circle stability, at the beginning, we are going to determine the location of the center. To determine the location of the center, as I said, from the center of the Smith chart to the edge here of the Smith chart, this corresponds to unity. Now, by scaling this value from unity to 1.59, so I'm going to measure this length and multiply it by the value of 1.59 to obtain the radius to CL. The location of CL is located at an angle 132 degrees from the x-axis. This is the x-axis. So I'm going to measure the angle from x-axis to 132 degrees. This would be 90 degrees here. 132 degrees at this point. It is located here, 130, 132. And I'm going to take a line from the origin of the Smith chart to this point and extend this line until this length from 0 to the point CL is 1.59 of this length from this point to this point. Okay, so this is the location of CL. Once I obtain CL, I'm going to draw a circle with a radius RL. The radius RL, sorry, is 0.915. The radius of RL is 0.915. 0.915, effectively, as I mentioned, the unit here is from the origin to this point. So I'm going to take this distance and multiply it by ratio 0.915 to determine the value of RL. And then I'm going to draw this circle. Alright? Now, I have already drawn gamma load circle, which correspond to gamma input equal unity. If the value of gamma load is 0, if the value of gamma load is 0, gamma input, it would be the magnitude of S11, and the magnitude of S11 is less than unity. This means that the region outside this circle will have gamma input less than unity. So any load impedance outside this circle will correspond to a stable amplifier. So any point here, any point, all this region here, any point, all this region, any impedance located at in this region will correspond to load impedance, which makes the amplifier stable. On the other hand, any impedance inside the unit circle here, the shaded region here, any impedance for the load impedance in the shaded region here will correspond to unstable amplifier. In a similar way, we are going to calculate the source impedance circle. Uh, the center of the source impedance circle, as we have mentioned in the previous video, is S11 minus delta S22 conjugate, all of them is conjugate, over S11 squared minus delta squared. This is the value of S11. Actually, I'm not talking about value. I'm talking about the complex, the complex value minus delta. Delta here is complex value, not the magnitude only. Here delta S22 over S11 squared, the magnitude, minus the magnitude of delta squared. From this, we find that the center of the source impedance circle is 1.09 with an angle 162. In a similar way, the radius of the source impedance circle will be the magnitude of S12, S21 over S11 squared minus delta squared. From this, we find it is 0.205. As we have done in the load circle, we are going to do in the source circle. So in the source circle, to determine the location of the center, here from the origin to the edge here is unity. I'm not talking about unity, I'm talking about 1.09. So I'm going to multiply this length by 1.09. It would be this point, and this would be at an angle 162. So from the x-axis, I'm going to move counterclockwise until I reach the angle 162 here, and I'm going to extend a line from the origin to the edge of the Smith chart and extend it until I reach 1.09, the radius of the Smith chart. Now the radius of the source impedance is 0.205. So I'm going to take from the origin to the edge of the Smith chart this length and multiply this length by 0.205 to find out the value of the radius. From the center, I'm going to draw the circle of gamma source. So this is a circle of gamma source. Now, because the value of S22 is less than unity, gamma out, when Z source equals Z naught, or when gamma source is 0, in this case, gamma output would be S22. This means that the value outside the circle, the value outside this gamma source circle, the value outside the circle, gamma output is less than unity. And inside the gamma source circle, gamma output would be greater than unity. This means that the value of gamma source here will correspond to a stable amplifier, and the value of gamma source inside the gamma source circle here would be unstable amplifier. So the unstable region for gamma source, it would be the intersection here between the Smith chart and the gamma source circle. So it would be in this shaded region. Any value outside this circle, even here, for example, which is not suitable for gamma load but suitable for gamma source, this suitable for gamma source, but if I am using this value for gamma load, it would be unstable. So any value outside this circle, it would correspond to, for gamma source, it would correspond to stable amplifier. So by taking these pieces together, we can say that, okay, this circle for gamma load, this shaded region is the values of gamma load which correspond to unstable amplifier, and the remaining parts of the Smith chart correspond to gamma load which is stable amplifier. On the other hand, this is the stability circle for gamma source. The shaded region here correspond to gamma source, which is correspond to unstable amplifier. Any point outside this shaded region will correspond to gamma source, which correspond to stable amplifier. So the unstable regions are the shaded regions. This is how to determine the stability condition for the amplifier and the location for gamma load and gamma source, which makes this amplifier to be stable. Now we have discussed the power gain. We have discussed the stability condition for the amplifier. In the following video, we are going to design a real microwave amplifier, assuming that we are designing this microwave amplifier for maximum power. So see you in the next video for designing a microwave amplifier with maximum power gain.